In this podcast, we're going to start discussing the equilibrium constant, which is K. K is a helpful way to determine the state of the equilibrium, okay? Where exactly it is at that point in time as compared to the equilibrium. It is specific for each reaction and each temperature, and it is unaffected by the initial concentrations or by catalyst. All right, to calculate the equilibrium constant K, you need to understand the following right here. So if you had a reaction JA plus KB is in equilibrium with LC plus MD, where J, K, L, and M are the coefficients and A, B, C, and D are the reactants and products, this is how you would set it up. So it's essentially products over reactants, and you are raising the concentration to whatever the coefficient is in front of that reactant or product, okay? So that's essentially what this equation means. And the equilibrium constant K is unitless, so you don't have to worry about units with this one. All right, now we've talked about K before in kinetics, but the equilibrium constant, big K, is not the same as the little k rate constant that we use. So here's a little compare and contrast. So big K is thermodynamic, not kinetic. Okay, so it is not going to be controlled by kinetics. Whereas little k is kinetic, not thermodynamic. Okay, big K doesn't have units, though we'll often treat it as if it does. Big K is independent of the reaction mechanism. It is written from the products and reactants in the final overall reaction. So a mechanism is not anything that we care about when we're calculating the equilibrium constant K. Little k, rate constant changes with the temperature and with the catalyst. A catalyst would change the activation energy for the rate determining step. And with little k, you couldn't write the rate law until you knew the reaction mechanism and have identified the lowest step or the slowest step. And only the reactants could appear in the rate law. Here, products and reactants appear in the equilibrium constant, big K, but we don't include solids or pure liquids, only gases and aqueous. All right. And the value of big K depends on the stoichiometric coefficients of the equation to which it's referenced, whereas little k is on the slowest step of the mechanism. With little k, intermediates do not matter, so you don't even leave their concentrations in the rate law. So there's just a little compare contrast. So understand they are not the same, they are different. All right, now the value of our equilibrium constant K can tell us a lot about the state of the equilibrium. So if it's a big value for K, a large value, then we know that the equilibrium is product favored, which means that the reaction is going to make products. So the reverse reaction is not as prevalent. So when the equilibrium is achieved, most of the reactant has been converted to product. So at equilibrium, you will have majority product. Now, when you have a tiny value for K, this tells you that is a reactant favored reaction. Okay, so that means that when you reach equilibrium, you will have a lot of reactant and very little product. So most of the reactant will still be there, and you'll have very little that has converted to product. All right, how do you write an equilibrium expression? So we're going to do a little practice. So if you were looking at this one, all right, you would do products over reactants. So that would be NO and O2. And then you need to raise them to the coefficients. So that's where this 2 came from. And then over reactants, our reactant is NO2, and it should be raised to the power of 2. Okay, so that's how we got that expression. All right. Now, And when you're looking at reactions and then the reverse of that reaction, which is shown below, there is a relationship between their K, their equilibrium constant values, okay? So here you have products over reactants, and then you reverse the equation and then products over reactants. Well, you see that they're exactly inverses of one another, which means their Ks are inverses or reciprocals of one another as well. All right, now there's a bunch of different types of equilibrium constants that we can use, or KEQs. All right, and these are all of them and what they're used for. So it's important that you understand that these all mean the equilibrium constant. So Kc, that's the most general form, and basically it's used with molar concentration. Kp is partial pressures, and that's what you would use when working on a gas phase reaction. Ka is the dissociation of weak acids in water. Kb is the dissociation of weak bases in water. Kw is the expression for the dissociation of water into ions, and Ksp is used for the dissociation of ions into water. Okay, so we're talking about aqueous solids at that point. All right, so here's a little practice. All right, so the first thing it wants to do is write the equilibrium expression, no concentration values. So it just wants us to write the actual expression. So products over reactants. So our products are NO2, and there's a 4 in front, so we're going to raise it to the 4. And H2O. Whoa, my pen started dragging there for a second. All right, and that's raised to the 6th. All right, and then that's all of our products. And then over our reactants are NH3. Whoa, I don't know why my pen's all of a sudden dragging. It's having some issues. And that's raised to the 4th. And then you have O2. And that's raised to the 7th. Okay? So that is the actual equilibrium expression for this reaction. Now it wants you to actually get the value for K. So you need to plug in all of the concentrations right there into this reaction, and then you'd multiply the top and multiply the bottom. When I did all of that, I got a K value of 130. Okay? And based on that value, that tells us that this is a large value of K, okay? It's pretty big, 130, which means that it is product favored. We would see mostly reactants that had been converted to product at equilibrium. All right, a little bit more about calculating K. When we're calculating K, pure liquids and pure solids are considered to have concentrations of 1, and therefore do not appear in the equilibrium expression. Only gases and aqueous solids appear. So if we were looking at the following reaction and asked to write an equilibrium expression, we would have to be looking at only gases and aqueous. So essentially, this solid and this liquid do not matter. So it'd basically just be the product of Cl2, and that would be the entire equilibrium expression.